So good morning. My name is Pierre Krieger, as you can see on the side. You probably know me as this little character here. That's my online identity. I'm not anonymous, but that's how everyone knows me. And I'm going to introduce you to libp2p and to showcase more or less how it works. So first of all, what is libp2p? libp2p is a protocol and a framework that lets you easily create decentralized peer-to-peer network. Originally, that was the networking stack of IPFS, and if you don't know what IPFS is, just ask your neighbor. I imagine that like 2/3 of the people at least know what it is. And then it got extracted into its own first-class project, so that people other than IPFS could use it. We have implementations in JavaScript and Go, and one in Rust. That's the one I'm doing, so that's the one I'm going to present the most. That's the one I know. And also implementation in Python, C++, NIM, and Java that are in progress. Like a lot of libp2p people are in the room, so I kind of hope that you can correct me if I'm wrong. But I think I got them all. It's used primarily by IPFS, as I mentioned, but also by Substrate and Polkadot, which are the projects that my company Parity is doing. It's also going to be used by Ethereum 2.0. And many other projects, maybe Matrix, the Matrix protocol, Riot, if you know about them. They are kind of thinking about it, maybe in the distant future. And now let's see how it works. So at the beginning, you have a node named Alice, but in peer-to-peer networks, nodes don't have names like Alice. They have private and public keys. So you start by generating a private and a public key. And your identity is the hash of your public key. Then this node wants to join a network. In order to do so, you have three possibilities. Bootstrap nodes, hard-coded identities for your network that you put in every client implementation. MDNS, you discover through UDP the other nodes that are part of the network. Or Bluetooth. So I put Bluetooth here because I have a prototype for libp2p. I'm going to talk about it a bit later. So you know about a node you want to connect to. First step, you establish a TCP connection. Second step, you try to negotiate the encryption. So we have this protocol in libp2p named Sek.io. We negotiate it. Do you want to use Sek.io? Yes, let's do Sek.io. And then we perform the handshake. So it's a traditional TLS handshake. Here's your public key, here's your ephemeral key, and boom, everything's encrypted. You derive a key for symmetric encryption. Step 4, you use multiplexing. Same principle. Which protocol do you want to use? Let's use Yamux. Yes, let's do Yamux. And then optional Yamux handshake. And that's how we establish a connection between two libp2p nodes. At the end, you have encryption and multiplexing over TCP. But there is a twist, which is that libp2p is more generic than that. libp2p is generic over the concept of transport. So in the example I just presented, I showcased TCP/IP, but libp2p can use anything. It can use TCP/IP, can use QUIC, Tor, Bluetooth, whatever you want. It's not tied to TCP/IP. That's one of its huge strengths. The only constraint is that they must be reliable and ordered. For example, you cannot use UDP. A lot of peer-to-peer networks use UDP, but we don't because of that. It's generic over a concept of a multi of the IP address. So you have TCP and IP addresses, and similarly you have transport and multi-addresses. That's the abstraction on top of it. It's best shown through examples, so that's like a TCP/IP address, IP4/UIP/TCP/report. But you can use DNS, you can use QUIC on top of UDP. You can use IPv6, obviously, with WebSockets, for example. You can use Bluetooth, you can use anything you want. And that's the generalization over an IP address. Similarly, as I showed, we are not tied to a specific protocol. Every time we establish a connection, we decide, do we want to use Sek.io, do we want to use Yamux, or do we want to use something else? Every time you establish a connection, you ask, hey, can I use this protocol? Answer yes or no. If the answer is no, you may try another one. In practice, every single network has some hard-coded protocols, but you can basically upgrade your protocol to a different one. So if you want to upgrade from SecIO to, say, TLS 1.3 or something, you can just add support for TLS 1.3, and the negotiation process, we use TLS for your new versions while keeping support for SecIO. And after a while, you remove support for SecIO. Thanks to this negotiation that happens at every single connection, you can upgrade your protocols without any downtime. It's also generic over a key pair format. We are not tied to ED 25519. For example, you can use RSA or SecP. Obviously, depending on the network, you can refuse the formats you don't like. For example, RSA. You may not want to accept RSA connections, but theoretically, libp2p supports them, and you can use them. The way this works is that the format of a public key is transmitted over time alongside with the public key itself. And similarly, the advantage is the same. You can upgrade to new curves. If we ever find a vulnerability in ED 25519, for example, we can upgrade to a new one. And that's something I already presented. I'm sorry, I don't have internet, therefore I'm looking at old slides and I'm kind of discovering because I don't have the changes I made since then, but that's okay. So seamless upgrades, you can add support for new protocols, remove the ones you had before, and then upgrade. This is the list of protocols that libp2p supports at the moment. TCP/IP, obviously, with the multi-address that corresponds. WebSockets. So why do we support WebSockets? So that you can create a node in the browser that connects to libp2p nodes through WebSockets. Similarly, WebRTC. That is here, sorry. WebRTC, same principle. From within the browser, you can connect through WebRTC. DNS, obviously, that's not very decentralized, but in practice, that's very much needed right now, DNS. Unix domain sockets, you can make two nodes connect if they are on the same machine, very useful for RPC requests. However, don't accept Unix domain socket addresses from the internet. You don't want someone to tell you, hey, my node address is this file, and let your node read the file that's been given to you. That's a bad idea. As for the encryption protocols, we have SecIO. It's a homemade protocol which should be replaced by TLS 1.3 at some point because you don't roll your own crypto. But it's used right now by IPFS and Substrate and Polkadot. Oops, sorry. It's used right now by us, but we know it's bad, and we're going to change it to TLS 1.3. Noise, that's a prototype in the Rust version of libp2p, but it's still pretty much unclear exactly which handshake we're going to use, and so on and so forth. Plain text, to be exhaustive, it's an encryption protocol that doesn't do encryption. Do not use that. As for multiplexing, we have two protocols, Mplex, it's also a homemade protocol designed to be simple to implement, and Yamux, which is made by HashiCorp. So I'm not a Go person, I don't know what HashiCorp is, but they seem to know what they are doing, and we are using them. We're using the protocol, I mean. As for the transport, there's a prototype for using QUIC. QUIC is this thing designed by Google that's soon going to become an IETF standard, I think and I hope. So if we use QUIC, we do not negotiate encryption and multiplexing because that's handled by QUIC itself. Is that me? No, that's the thing. Battery is low. But in the long term, libp2p would use QUIC by default. As for the transport, you have Bluetooth. That's just something I mentioned because it's cool, not because it's usable. But eventually, you should be able to connect to nodes that are near you physically thanks to Bluetooth. And I'm sorry I put this in this talk because I'm excited by that, but you cannot use that yet. But it showcases the flexibility of libp2p. You can just put Bluetooth in the stack. So let's get back to our node. As I demonstrated, you establish connections to other nodes that you know of. You are now connected to all your Bootstrap nodes, assuming you have 4 Bootstrap nodes, that's 4 connections. What lip2p does is at a periodic interval, you identify the nodes that we are connected to. So that's a zoom of the previous slide. The way we do that, we open a substream. So remember, we have a multiplex connection. We open a substream. Hey, please identify yourself. Answer, I'm Rust IPFS version 0.1. Rust IPFS doesn't exist. That's just an example. The node also responds with the list of addresses it's listening on. I'm listening on the following addresses, 81.2.95.29, port 13333. I'm also listening on this, I'm also listening on that. The other node also responds back with the IP address of the requester. So this node tells this node what this node's IP address is. That's like the lip2p equivalent of the stun protocol. Except we don't use stun, we use this mechanism. You ask other nodes through a lip2p protocol what your IP address is. And after that, the substream is closed. I mentioned that the substream is closed because substreams are ephemeral. They are not long-lived, they are very short-lived. Every single request you make, you create a new substream, you do your query, and then you close it. It's not something that you keep alive forever. Another example of that is that we periodically ping connections to see if they are still alive. So we open a substream, ping, pong, okay, the connection is still alive, we kill the substream. The advantage of doing that is that requests and responses are automatically mapped. If you know you send a request on a specific substream, you have the answer on the same substream, you don't have to associate the two, which removes a lot of logic from a higher level of the code. And it also allows distributing substreams along multiple connections. You can theoretically open 4 or 5 connections between 2 nodes and have your substream being distributed between the 4 or 5 connections. So let's continue with that. We're connected to our Bootstrap nodes. We ping and identify periodically. But we have to discover the rest of the network. All the nodes around us are not. We have to discover them somehow. Similarly to encryption and multiplexing, the discovery mechanism of lip2p is generic. You can plug your own. So right now we only support Kademlia random walking. But you can theoretically plug your own in Rust. In more specifically Substrate, we had a prototype of something like Brahms, which we could just plug in the design of lip2p, and that was like just a prototype, but it kind of showcases the flexibility of the thing. If you don't know Brahms, it's a simple discovery mechanism that's designed to be Byzantine resistant. You can Google that. So just to introduce quickly to Kademlia, I suppose that most of the audience have heard about Kademlia. Very, 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 very simply, you ask a node what his neighbors are, and the node answers with the node it knows that are near it. And then you can connect to them. Very, very, very simply put. Similarly, for gossiping, the mechanism is pluggable. We are not hard-coded to a specific mechanism. We have 2 protocols named FloodSub and GossipSub, but you can also create your own. Same principle, very flexible. I have 2 slides that are the same. Sorry for that. A frequently asked question about lip2p and peer-to-peer networks in general is what if you're behind a NAT? So a NAT is your home router, for example. If a node tries to connect to you, if the node XD7 tries to connect to G7A, it's not going to work because the NAT doesn't accept the TCP connection. Also applies to browsers. So one use case of lip2p is being able to have a node written in JavaScript that speaks lip2p, and browsers don't accept incoming connections, unfortunately. You cannot go through this barrier of Firefox or Chrome. And the solution to that lip2p provides is relaying. So how does that work? Step one, the node that is behind the NAT dials another node. If you're in the browser, that's through WebSockets or WebRTC. If you're not in a browser, that's a typical TCP connection. You make your ongoing connection. Then when someone asks this proxy, who are your neighbors, the proxy is answering, hey, I have this thing connected to me that wants relaying. And thanks to that, the node here can ask for relaying. It can ask for a direct connection. This is done similarly through a substream. We open a substream with a proxy, and the node opens a substream to the relay node and transmits all connections, all communications through them. And on top of that, we also negotiate encryption in order to avoid man-in-the-middle attacks, because that's a very obvious man-in-the-middle, and we don't want it to be able to read our communications. Now let's dive a little bit more into the design of Rust DP2P specifically, because that's the implementation I'm working on. A few words about Rust, first of all. Rust is fast, it has no runtime, it can talk to C, it has zero-cost abstractions, you can abstract over something without any runtime overhead, which is extremely cool. That's the same thing as C++, you don't pay for what you don't use. Rust is safe, it doesn't have any undefined behavior. Everything you do is, it can have undefined results. You can have a calculation for which you don't know the result in advance, but it doesn't have any undefined behavior. It cannot accidentally launch a missile, for example. That's something that Rust prevents. Everything you write for your code needs to be proven to not trigger any undefined behavior. Needs to be proven to a compiler for your code to compile. And Rust is cool. Source on that, it's the most liked programming language according to Stack Overflow. So it's not me saying it's cool, it's the audience of Stack Overflow. I also think it's cool, but I'm not a reliable source for that. And these three things make it the perfect language to write networking code. Networking code is very vulnerable to untrusted input, obviously. Anything you can receive, you receive is untrusted. And so the last thing you want is untrusted input being able to trigger an undefined behavior, and Rust prevents that. So as a general overview of Rust DP2P, I kind of want to say that Rust DP2P is robust. We are extremely proud of Rust DP. Well, I am extremely proud of what we did in Rust DP2P. I hope the people that worked on it are proud as well, but I am. If we have a networking bug in Substrate and Brocalat, which are the two projects that use Rust DP2P right now, we are kind of 98% sure that it's not coming from Rust DP2P and that it's coming from the upper layer of that because of its robustness. If you know the Tokyo, Hyper, and Hyper libraries, for example, in Rust, they are like the same level of robustness, in my opinion. And Rust DP2P is moderately stable, which means that we still break APIs, but we are trying to do it as little as possible, and we maintain a change log so that you don't have to figure out yourself what has changed. Rust DP2P is WASM-friendly. WASM-friendly, by that I mean compiling for the browser. You can Rust, depending on your knowledge of Rust, you may or not know that, but you have this command cargo web. And if you run cargo web build in the Rust DP2P repository, it just works. There's no trickery involved. You run the command and you get a WASM file. That's only available since the latest version. And this WASM file runs in the browser. How we do networking through p2p-wasm-ext crate. So you write your transport layer, for example, WebSockets. You write a small compatibility layer between Rust DP2P and the browser API. You write that in JavaScript, and you plug that, you give that to Rust DP2P, and it can use that. And one thing I've been working on for the past couple of weeks is compiling a blockchain-like client written with Substrate for the browser. Normally, there's no technical obstacle to that. In practice, that's less true than it is in theory. But I should be done eventually, and it would be extremely cool to have an actual blockchain node running in the browser. I don't think anyone has done that before. So I'm extremely excited as well. Rust TPP uses asynchronous Rust. So I'm going to explain briefly asynchronous Rust. The main library for that is named Tokyo. It's what handles networking and task handling. How your thread behaves. First of all, each socket, each connection to a remote has its own task, which is a coroutine. If you know that in JavaScript and Lua, a task and a coroutine are the same. So each socket has a coroutine dedicated to it. The data of the coroutine is on the heap. When the coroutine needs data from a socket, it registers itself, hey, I need data from this socket. Then it yields, you go out of the coroutine. Then the thread runs epo, looks at the result of epo. For each descriptor that epo says there's data available, we look the corresponding tasks. Hey, these tasks were waiting for data. We add these tasks to a queue of tasks to execute. Then the thread picks at the queue, pulls things to execute, runs the coroutine, the tasks to execute, which register themselves again if they need more data, and so on. And we loop like that forever until nothing's ready anymore, and then we wait and we run epo. This system cooperating multitasking in Rust specifically is extremely fast. So that's a blog post from 2016. Unfortunately, I don't know anything newer than that, but that showcases asynchronous Rust. So higher is better, and the first one is Rust. That's all you need to know. So you have JavaScript at the far, not the far right, sorry for that. You have JavaScript. I didn't say that on purpose. You have JavaScript the slower and Rust the fastest. I would be extremely curious to have a new benchmark, because that's very old. And even though I'm defending Rust and Rust is the best here, I'm not sure if this is extremely reliable. I would be glad if someone wrote something more recent. So how we organize that in Rust P2P specifically? We have one task per network connection. So every time you want to read or write data to that connection, this is done through this task. This task also handles encryption, multiplexing, and parsing, so all the low-level stuff. And it translates that into higher-level events. For example, academia response has arrived. And these higher-level events are then sent to a main task. We have a main task that synchronizes all of this. It's a state machine and pulls events from the task dedicated to each socket. And it synchronizes that in flat way so that you don't have this spaghetti of events. This happened before this, but then this conflict. So wait, what do we do now? I'm confused. Nothing makes sense anymore. We don't do that. We process events one by one. And if something is weird, we just kill the connection, which should not happen, but that's how we handle weird situations. Illustration here. Oh, that's not very readable, but you have one task per connection on the right, communicate with the internet, and the main task is pulling this and synchronizes all of this. So if two nodes want to talk to each other, this task sends a message to the main task, which then dispatches it. There's no direct communication. There's no sending an event from this to this, for example. Everything goes through the main task, which eliminates a lot of logic issues. That's what I just said. Eliminates a lot of logic issues. And that's a very flexible design. Rust TPP in general has a very flexible design. Fun fact, Rust TPP can be turned into an HTTP server. Why did we do that? Because it's only 300 lines of code. There's no reason for doing that other than fun. We're not going to use Rust TPP for HTTP. but it allowed us to compare REST P2P with other implementations of HTTP, because otherwise we wouldn't know what to compare it to. So I didn't draw a graph, but that's like the best REST libraries that exist. 230K requests per second, HTTP requests per second. REST P2P is only at 156K, but that's kind of okay because we are not optimized for HTTP at all. Go is behind at 132K and Node.js 32K. I'm happy with these results because it showcases that we didn't make any decision that made it not fast, basically. It could obviously be improved, but I'm happy with that. In conclusion, the keyword of libp2p is the modularity. As I showcased, you can plug your own encryption, your own multiplexing, your own transport. You can use your own discovery mechanism, your own pub/sub mechanism. We provide some, but you can design your own if there's a need, which is a huge plus. And the keyword of REST P2P is performance. We made it fast. We made it as fast as possible. And I'm happy with the results. And that's it.
How close are you now, just for the benefit of the crowd, how close are you now with the implementation of libp2p Rust versus the more mature Go version?
So there's some stuff that the Rust version doesn't have, most notably gossip/sub. Gossip/sub is like the prime pub/sub mechanism, which is the one you're supposed to use. We don't have that in Rust because in Substrate and Polkadot, which are the things that we're basing on top of it, we are not using this. We're using like a homemade pub/sub thing, so we didn't implement it. That's like the major point that's missing. Relaying, so I presented relaying going through a proxy that's also not in REST P2P. We removed it at some refactoring a very long time ago. And I kind of re-implemented it, but haven't finished yet. And I think that should be it. Other than that, they should just talk to each other without any issue. Yep.
Yeah, so the things you implement on top of libp2p for Polkadot, are they also built into libp2p, like as an extension, or are they built on top?
So right now they are like, so to explain a bit more into details, right now we have a libp2p protocol designed for Substrate, and within that we do our own thing. So that's kind of opaque and it's not defined at all. Eventually in the future, we want to build that directly on top of libp2p. But that requires some refactoring in Substrate and Polkadot, but that's the plan. But it's not going to happen anytime soon, but that's the plan, yes.
If two nodes are introduced through a relaying node, do they always talk through that relaying node, or can they upgrade their connection to a direct connection if they negotiate that?
Well, theoretically, they could just connect to each other through a different way. The point of relaying, however, is to handle situations where you cannot connect to each other directly. So, yeah. But you can use relaying even if you can theoretically connect to each other. Yep.
I would add also that relaying is kind of the first step towards packet switching. Like someday we would like to have a packet switched set of connections, but that's like a far future thing.
I must mention that not half of the room, but there are a lot of protocol apps people in the room that know more about the general direction of libp2p than I do.
Is there a maximum number of connections for a relayer node to connect other nodes?
So since we haven't implemented relaying in Rust, the answer is not a number. For Go and JS, I don't know.
I can speak to that. We are currently stress testing in a very vertical scaling fashion, like what the throughput of the reading node is. So we've been making, this is for Go libp2p, we've been making a huge amount of fine-tune improvements and so on. Yeah, we are currently handling around 130,000 connections per relay, and we are just, there are some bottlenecks and so on that we're working towards, but it's just gonna get better. And at one point, there's gonna be a federated relay infrastructure as well. We're gonna introduce a few mechanisms in the protocol so that the relay can also put back pressure on clients that are attempting to connect to relays and kind of like introduce them to an alternative relay. We're gonna be using relay as well as a signaling mechanism. So if you have two nodes that need to connect to each other, but then suddenly they discover that they can peer through the NATs and establish a direct connection, there should be kind of like an escape hatch as well to upgrade that connection to a direct one. So yeah, there's a big roadmap. So if you're interested in that, speak to them.
I'm also just curious. That's really cool. When do you guys expect that to land? Do you have
We
some
need your
rough
help.
idea?
We need your help. We need your input. We need your feedback. These are ideas. This is vision from the Lib2P team, and really the community is open. So we're happy to get your feedback, to find people who are excited about even implementing these aspects or defining the protocols for them. So definitely speak to us.
Is there a branch?
We can speak that.
Is there a branch people can check out?
Sorry?
Is there a branch people can check out?
There is a roadmap. There is a document with many of these ideas. There is. I think the best place right now is to look at a roadmap and to basically participate in the community.
Cool.
And yeah, basically find a way to accelerate this work, because there's a lot of ideas that we need to make it into the presentation.
Yeah, Raul is the technical lead of Lib2P, so don't hesitate to talk to him.
You mentioned WASM stuff. On the browser side, the transports, you're still using the JS transport, right?
So that was the initial plan. Then I talked to someone from Protocol Labs, I don't remember who basically told me it's a better idea if you just write your own interfacing thing. So the initial plan, just to explain to everyone, was to have Rust use the JS transport, the transports written for JS Lib2P. But I changed that idea to have our own API, and you rewrite the interfacing between the browser and our API.
Did you find any critical problems that made you make that decision?
Yes and no. Well, it's more like the APIs are kind of different in some way, and it's kind of annoying to make them the same. Yeah. Well, the API of JavaScript and the one of Rust have some differences that, while not critical, require some hackish thing, and nothing critical, but kind of not great at the same time.
I'd also add that multiplexers in general have all kinds of really hard problems and feature sets that vary. And so it's useful to be able to use the multiplexer that works best for your protocol and application, because we've tested a whole bunch, and they vary a lot. Some introduce huge memory overheads, some don't have back pressure, some have bad QoS, or will randomly close streams. All kinds of things happen. You would think that multiplexers would be easy, but they're not. And so there are very simple ones, there are more complicated ones. Your protocol and application will probably want to pick the one that works best for them. You can benchmark this.
I must mention that from the Rust point of view, writing a multiplexer is one of the hardest tasks I've ever done, maybe. It feels extremely easy, but so combined with asynchronous Rust in particular, you need to notify the right task when data arrives on this specific stream, and so on and so forth. Much harder than it looks.